going to start Chapter 12, and Chapter 12 looks at the idea of probability. It's not quite as geometric as some of the stuff we've been doing. However, we will, by the end of this, incorporate a fair amount of area and other type of geometry problems. So it's going to relate. But there's a lot of probability and things like that on standardized testing, including the ACT. I think a lot of you have mentioned that you saw it on your Aspire tests as well. And frankly, we often just run out of time before we're able to teach it. So this might run just a little bit long today, but it's pretty important that you get a basic understanding of probability. So let's look at our first little example. Let's dive right in. You flip a coin and roll a six-sided die. How many possible outcomes are there in the sample space? A sample space is basically a list of all possible outcomes. Okay? So how do we do it? How do we create a sample space? How do we know what all the possible outcomes? What we want to do is we could list all our outcomes. We could draw a picture to do the outcomes, or we could do something of that nature to try to indicate the outcomes. The trick is to be systematic about it. Okay? We don't just want to start randomly listing outcomes without having some sort of system, because we're probably going to miss something. Like, I don't want to say, well, I could get maybe, let's think, I could get a heads and a 3, or I get a tails and a 4, and a heads and a 1. And if it's all random like that, we're probably going to miss things. So you want to be systematic. So a lot of different ways we could do this. We could just kind of make a list, a systematic list. So why not try, we could make a list. Let's say I could have a heads 1, heads 2, heads 3, heads 4, heads 5, and heads 6. I could also have a tails 1, tails 2, tails 3, tails 4, tails 5, and tails 6. Those are all the possible outcomes of flipping one coin and rolling one die. This would be my sample space. It lists 12 possible outcomes. All possible outcomes are listed. Now that's a perfectly good way of doing it. Another way of doing that could be drawing a picture. So, I mean, some people like to draw a picture. So instead of just writing heads 1, they'll like write heads. See, there's heads. Little person there. And a 1. And then the heads, and then they do another die with a 2. Okay, so some people draw pictures. They're more artistic. Not my choice. I'd much rather just write numbers and lists. But another good way of doing it is using a tree diagram. My first outcome could be heads or tails, and then each one after that, you get a 1, 2, 3, 4, 5, or 6. 1, 2, 3, 4, 5, 6. And I've got 12 different outcomes down here. Heads 1, heads 2, heads 3, heads 4, heads 5, and heads 6. Okay, so it's another way of listing my outcomes, another way of creating a sample space where I diagram what's going on. Now, this can get handy when we start getting more complicated ideas. In fact, this is a technique that gets used even in AP stats. So something you want to think about as you're creating sample spaces. So you want to know what all the possible outcomes are. So list all the possible outcomes in a sample space, then find the number. Actually, I'm going to list the possible outcomes and then find the number. I'm going to do it backwards. Flip 2 coins. Okay, first coin could be heads or tails. Second coin could be heads or tails. And then heads and tails again. So my possible outcomes are heads, 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 tails, tails, heads, and tails, tails. Those are my 4 possible outcomes. Okay, notice each outcome is one branch of the tree. Okay. Flip 2 coins and roll a 6-sided die. Now this is going to get a little more interesting. This is where a tree diagram can be very handy because we're going to get quite a few outcomes here. My first outcome is a heads or a tails. Since I'm flipping a second coin, then I get heads, tails, heads, tails. And now, after each one of these, I get 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. How many possible outcomes are there? Well, if I go across the bottom row here, because that's where I count my outcomes, I have 6, 12, so 6, 12, 18, 24 possible outcomes. I could then list them if I wanted to. My first would be heads, heads 1, heads, heads 2, heads, heads 3, heads, heads 4. Okay, and we could keep going and get all the possible outcomes of the list as well. But here we can see where a tree diagram is much faster than the listing. Okay, for this example, example 1, the tree diagram wasn't especially faster. For example 2 here, much faster to do the tree diagram. So you can see as things become more complicated, tree diagrams can definitely be the way to go. The probability of an event, which, by the way, this is important notation, P of A, the event is event A. Okay, so A is a variable that we use to designate an unknown event, equals the number of ways you get your desired outcome over the total number of possible outcomes. All right? Now, this is simple probability, and you've done stuff like this before. It's not that earth-shattering. For example, a pouch contains 5 white rocks, 8 black rocks, and 2 brown rocks. If drawing blindly, what is the probability of getting a black rock? Now, again, I want you to note what we're saying here. The probability of getting a black rock. So I've now named my variable. Instead of just saying A, I've said what exactly I'm looking for the probability of. So the number of ways you get your desired outcome over the total number of possible outcomes. Now this is a very simple problem because all we're doing is drawing 1 rock out of a bag. And I want to know the probability of a black rock. How many black rocks are there? There are 8 black rocks in the bag. Out of how many total rocks in the bag? How many possible outcomes are there? Well, I could get 5 white, 8 black, or 2, so there's 15 possible outcomes. So my probability of getting a black rock is 8 out of 15. Now we could decimalize that. It's a little more than half, 8 out of 15. In fact, if I take that as a decimal, is 0.5333, or 53.3%. So I could make that as a fraction or as a percent. The nice thing about the fraction here is it's an exact value, where the percent is an approximate value. We do have to watch that to make sure we're getting exact values and not approximate values whenever possible. For the previous example, 2 coins are flipped and a die is rolled. What is the probability of getting exactly 1 heads and a 4? Well, let's go back to my sample space. Here's where my sample space can be really useful. I want exactly 1 heads and a 4. So when I go back to my sample space, I notice that I had 24 possible outcomes. So my probability of heads and 4, the total number of outcomes possible is 24. We already know that. How many outcomes have exactly 1 heads and a 4? Well, we got to kind of look at our tree. If I start here, I got a heads. If I come over here, that's not going to help me because that's a second heads, and I want exactly 1 head. So nothing down here is considered successful. But if I have a heads and then a tails and then a 4, I do have 1 branch that gives me exactly 1 heads and a 4. So there's 1. Here I start with a tails. That's fine. If I go over to tails again, that's not going to give me exactly 1 head, so that's not going to help me. So I'm going to have to come down here, down this branch, and then a 4, There's another branch. I have 2 branches in my tree that give me exactly 1 heads and a 4. So my probability is 2 out of 24 or 1 out of 12. We usually reduce our fractions to lowest terms here. Okay? So we're calculating some probabilities now. Here I have a sample space that's given to you, and it's all the possibilities of 2 dice being rolled. Okay? So I'm rolling 2 dice, and these are my entire sample space. How big is my sample space? How many possible outcomes are there? That's always my first question. Well, I have 1, 2, 3, 4, 5, 6 columns and 1, 2, 3, 4, 5, 6 rows, so that gives me 36 outcomes. Okay, there are 36 possible outcomes. The first asks, what is the probability the sum is not a 6? All right. Well, it might be easier since I got 36 outcomes rather than counting all the ones that aren't 6s. Let's count the ones that are 6s and subtract that from 36. So where do I get a 6? Well, 5 and a 1 gives me a 6. 4 and a 2 gives me a 6. 3 and 3 gives me 6. 2 and 4 gives me 6. And 5 and 1. Those are my 6s right there. Okay? So I have 1, 2, 3, 4, 5 outcomes that give me a 6, which means 31 do not give me a sum of 6. So the probability is simply 31 out of 36. P not 6 equals 31 out of 36. And notice, I'm not just writing the answer down here. I'm saying what it is. P not 6. How about the sum is less than or equal to 9? This is what I'm going to have you do on your own. So count how many are less than or equal to 9. Now, instead of counting how many are less than or equal to 9, it might be a lot easier to count the ones that are 10 or more and subtract that again, right? So I'm going to have you do this one as one of your questions for today. I can't get that to work. There we go. Geometric probability is very similar to what we were just doing. The geometric probability is followed by finding the area of the desired outcome over the total area. So with geometric probability, instead of doing a sample space as far as listing all the possible outcomes, we use areas or sometimes lengths to determine a probability. In other words, it's still, though, desired area over total area or desired length over total length. Okay, it could be desired volume over total volume. Any measurement like that. But now we're using our geometric concepts to do that. So I have a dartboard drawn in here. The radius of each circle is 3 inches, 6 inches, 9 inches as it gets bigger. A person throws a dart at the board. Shown, since the person is not skilled at darts, the dart is equally likely to hit any point inside the square board. Are they more likely to get 10 points or 0 points is the question. So what we'd have to do is find the probability of getting 10 points and the probability of getting 0 points. Again, since throwing a dart is normally a skill-based thing, the outcome normally wouldn't be random. So in this case, we're going to assume that the outcome is random. If someone is skilled at throwing darts, obviously the outcome is not random. Okay, so I'd have to find the probability of getting 10 points or 0 points. So probably the 10 points, let me make a skinny pencil, I'll need this. The probability of 10 is going to be the area of the 10 circle over the total area of the square. Sorry, it's supposed to be a square. Well, the area of the 10 circle has radius 3 inches. Okay? So the area of the 10 circle is simply pi times 3 squared, which is 9, so 9 pi inches squared. The total area will be the area of the square. Now, the half this here, that we know that that's 9 inches. So one side of the square is 18 inches. So 18 times 18, 324, I think. But I'm going to double check that to make sure I get that number right, because my brain is kind of, yeah, 324. And since we're calculating a probability, notice the units cancel out. So units are no longer an issue here. So now I take 9 pi. So my actual probability exact value would be 9 pi divided by 324. But I can simplify that, or at least express it as a decimal. Usually we do in geometric probability problems. So 9 pi divided by 324 is 0.0876, or okay, or 8.766% chance of getting in the bullseye in the 10 circle there. Okay, that's the probability getting a 10. The probability getting a 0, again, area problem. The total area is still 324. Okay. But now I have to find the area that's 0. The 0 area would be the area of the square minus the area of the big 2 circle. Okay? The area of the square is 324, we know that. Minus the area of the large 2 circle, the yellow circle and everything inside it, that would be radius of 9, so it's 81 pi. So there's my exact probability, but again, I'm going to do that 324 minus 81 pi first. 69.53 over 324. So 69.53 divided by 324 is about 0.2145 or 21.46%. Clearly, we are much more likely to get a 0 than we are to get 10 if throwing randomly. Okay? More interesting is the second problem here. Are we more likely to get 10 points or 5 points? Well, we know the probability of getting 10 points already. P10 we know is 8.76%. What we do have to find is probability of getting a 5 point. Okay? And again, our desired area is going to be the trick here. How do I find that desired area? The desired area is going to have to be the area of the 5 circle minus the area of the 10 circle. Because I just want to be in the green, but not in the pink. Divided by, and then that's divided by the total area, still 324. So I'm going to leave the rest of that problem to you to figure out. And you tell me, you'll see by the multiple choice what information I'm looking for. The complement of an event is simply the 1 minus the event itself. So if the probability of getting A is 0.45, the probability of A bar, notice how we notate it, A bar means a complement, is 1 minus 0.45 or 0.55. This would be 1 minus 1 or 0. This would be 0.97. 1 minus 1/4 is 3/4. So that's a really simple concept. If you run into those problems on the homework, those would be really super fast. If I know the probability of an event, the complement of the event is probability of that is 1 minus that. By the way, a probability can never have value more than 1 and less than 0, just so you know. And one simple problem to finish up. It says 2,184 adults were surveyed, so that's good to know, so I don't have to add up the individual columns. It says 1,328 of them had pets, had at least one pet. The types of pets are shown in the figure. What is the probability that a pet-owning adult chose at random has a dog? Actually, the numbers I'm noticing here are not correct because the 916 plus 677. This is a book example. It's 146 plus 93. That's 1832. So this number should be 1832. Okay. Actually, I'm going to go with the 1938 in further review because 1328 are the people who have at least one pet. Some might have multiple pets. So you might have 916 people who have dogs, but they have a dog and a fish. So they would count in both categories. That's probably why the sum is different. But it's what is the probability a pet owning adult chosen at random has a dog? Simply, we take the desired outcomes, the 916, divided by the total number of adults with pets, which is 1328, and that's the probability of dog. Okay? Very simple, very set up, and again, we could put that as a decimal if we needed to. All right, that's probability. You're going to have some fun with this stuff today in class. A little geometric, but not horribly, and we'll see you in class.